Okay, so the next thing that we would like to calculate is what's called the path integral. Now what we would like to achieve is that, okay, so we have our particle is at the position r prime at the time t0, and we are talking about the propagator or the amplitude that at the time t it will be at the point r. Classically speaking, what we would say is that, okay, there is a path that the particle will take, and the particle will take, for example, such a path. Now, quantum mechanics tells us that you cannot really talk about paths. So, I mean, this description doesn't really make sense. But nevertheless, we can still talk about the amplitudes corresponding to given paths in quantum mechanics. That is what we will achieve. So basically, this is one path. This is, let's say, the classical path. But we can imagine other paths. You can imagine whatever you can imagine. I mean, they don't need to follow any type of equation of motion. Now, what we will show is that the amplitude for a given path is nothing but e to power I over h bar times the classical action for that path. Now, I repeat, this doesn't have to be a single path. That is the classical path, but it's just any path you can imagine that connects those 2 points at those 2 times. Just for that path, calculate the classical action. Classical action is just nothing but the integral of the action of the Lagrangian from t0 up to t. X and x prime are, of course, functions of time over here, with the boundary condition that, well, let me put the r. R at the time t is equal to t0 is our r prime, and r at the time t is what we denote by r. So we have those functions. You just put those functions in the Lagrangian, integrate over time, and then you obtain the action corresponding to that path. Now, of course, if you imagine and then the total amplitude for the particle to go from the initial position to the final position will be just sum over all paths of e to power I over h bar s corresponding to that path. Now, if you think about the h bar, the classical limit we can easily obtain from here also. If you assume that h bar is a very small quantity relative to some other dimensionful parameter, if h bar, we can even take the limit as h bar goes to 0. When you are summing over all these paths, well, you see 1 over h bar, it's highly oscillating. So you take one path, its action has a value for that path. You take some other path, S has a value almost equal to the action of the other path, but they differ very slightly. But due to this highly oscillating character, one will contribute, let's say, positive, the other one will contribute negative, so you don't get any contribution. But nevertheless, this assuming that S changes as you change your path very slightly. But there is a path for which even if you change your path slightly, S doesn't change. So for such a path, the contributions do not cancel. So you get a finite contribution to this amplitude, even in the h bar goes to 0 limit. And that path is defined by delta S is equal to 0. Have you taken classical physics? Yeah. So you're familiar with the action. So this is how the classical limit comes, another way of saying how the classical limit comes from quantum mechanics, assuming that the amplitude for a given path is determined by the action corresponding to that path. So that is what we will try to achieve, let's say. And the way we will proceed will be just use this composition property of the propagator. You see, we had already, where was it? This is the property that we will be using. Now this is what I will do. Let me just use this as my time axis, this as the position. Let's say my particle starts here at the time t0. This is my position r. It will be at this point at the time t. Now this tells me that to calculate the total amplitude for my particle to go from r0 at the time let me call the position r0, r0 at the time t0 to the point r at the time t, just take some time in between. This is what previously I called t1. Let me just take t1 over here. Then it is just the amplitude that at the time t1 it will be reaching this point r1 at the time t1, and then from the time t1 it will reach the point r at the time t. I just multiply those two amplitudes and sum over all possible values of r1. But that second amplitude that it starts from r1 and goes to r, I can also divide it. So I will just divide it over here once more. T2 another time, T3. Here I will have Ti. Here I will have Tn minus 1. I will just call T my Tn. So this is what basically I'm doing. I'm looking at this amplitude. RT, R0, T0. This will be equal to, well, I start from R0, T0. I go to R1 at the time T1. Then I start from R1 at the time T1, go to R2 at the time T2. Then I start from R2 at the time T2, and just like this, I eventually reach Ri at the time Ti. I start from Ri at the time Ti, and eventually I reach Rn at the time T. And of course, all these intermediate times I have to integrate over. So this is my propagator now. But you see, that integration is nothing but summation. So basically what we do is, at R0 I start from some value, at R1 there is another value, at R2 there's at T2 another value, at T3 there's another value, at Ti there is another value, at Tn minus 1 there is another value, and from Tn minus 1 I go to, at the time T there, I reach R. So these values of R1, R2, R3, they have a corresponding contribution. There is one amplitude corresponding to these values of R1, R2, R3, Ri, Rn. Then the integral just tells me that change those values. Let's say I'm integrating over, let's say, R2. What I will do is I will just keep R1 fixed, R2 it will have a slightly different value. R3 is fixed. All the rest are fixed. So these values of R1, R2, R3, they contribute a different value to my integral. I'm just summing all these contributions. But this means that, I mean, you see, these two, let's say, paths, they're paths. So each path has one value given by this product over here. Changing the values of Ri's at different times, they just correspond to changing my paths. And each path has this value, and I'm summing over all possible paths. So that's why I write this as this is equal to sum over all paths of this product. This is what we mean by path integral. Well, we will do a couple of more steps. You see, this path doesn't really resemble the classical path or any other classically thinkable path because it's not continuous. When we talk about path, we usually mean some continuously changing parameter with time. But what we will do is we will take the limit as n goes to infinity. So if we take the limit as n goes to infinity, we will be basically dealing all the path at every time, and hence it will become continuous. So that's more meant by what is meant by a path integral. So we will eventually take the limit as n goes to infinity. But of course there is a problem. So what do these factors become in that limit? So that's what we will look for now. Now let me look at one of those terms only. So I have, let's say, R2 Ti Ri plus 1 at the time Ti plus 1, Ri at the time Ti. And I will just assume that Ti plus 1 minus Ti is equal to delta T. I will just pick them to be equally spaced. Now this is nothing but, from its definition, Ri plus 1 e to power minus I over h bar Ti plus 1 minus Ti h. So this is just Ri plus 1 e to power minus I over h bar h of delta T at Ri. Now, for the Hamiltonian, I will just assume it has this form. Well, most of the Hamiltonians that we will be dealing with do have this form. Now, e to power minus I over h bar h delta T is not equal to e to power minus I over h bar p squared over 2m delta T e to power minus I over h bar h, now v or delta T. Because p squared over 2m and the potential, the kinetic term and the potential term, they do not commute. So that's why they are not equal to each other. But nevertheless, delta T is equal to e to power minus I over h bar p squared over 2m delta T e to power minus I over h bar v of r delta T plus corrections of the order of delta T squared. Now, in fact, I can do slightly better than this. This will be equal to e to power minus I over h bar v of r over 2 delta T e to power minus I over h bar p squared over 2m delta T e to power minus I over h bar v of r over 2 delta T plus corrections of the order of delta T cubed, if I wanted to. But just for simplicity, I will stick with the first expression. The second line is a better approximation than the first line, but the first line would be enough for me. And keep in mind that eventually I will take the limit as delta T goes to 0, hoping that all those corrections that are of the order of delta T squared, they will go to 0 in that limit. Now, within this first approximation, r e to power minus I over h bar h delta t. This is equal to r e to power minus I over h bar p squared over 2m delta t e to power minus I over h bar v of r delta t times r prime. Again, keeping in mind that there are corrections that are proportional to delta t squared. This is equal to, well, I can insert a momentum eigenkets right over here. Now here, this p squared and v of r, they are operators there. But p acting on a momentum eigenket just gives me the eigenvalue. So this will be equal to e to power minus I over h bar, p squared over 2m delta t, e to power minus I over h bar, v of r. Now this is just, r is again the eigenvalue, delta t, r, p. Just one correction here, I'm talking about Ri plus 1 and Ri. So this is Ri plus 1 p Ri. This is this matrix element. This is equal to dq p e to power minus I over h bar h delta t. Keep in mind, this h is not an operator anymore. I just replaced the momentum operator with the number p and the position operator with Ri. So that h is a function of the number p and the position Ri. No operators left. Ri plus 1 p Ri. This is equal to dq p over 2 pi h bar cube. Well, I know what these are. This is e to power I over h bar p Ri plus 1 minus Ri minus I over h bar h p Ri delta t. Let me write it in a slightly different form. So let's just review some classical physics. Do you remember how you define the Hamiltonian in classical physics? Hamiltonian was nothing but PQ dot minus the Lagrangian. Or Lagrangian is nothing but PQ dot minus the Hamiltonian. Let's look at the above exponential. We have Ri plus 1 minus Ri, that is the difference of the position of the particle at two nearby times divided by delta t, and eventually I take the limit as delta t goes to 0. Well, that is nothing but Ri dot, or q dot in classical physics terminology. So that exponent is nothing but the Lagrangian. In fact, up to this point, I didn't really need to assume anything about the form of the Hamiltonian. I mean, whatever the form of the Hamiltonian is, this matrix element is always given in terms of this such a factor, pq dot minus h. Plus, there will be corrections of the order of delta t squared. Now, let me take that p integral. If I assume that h it has this form, assuming h has this form, the momentum integral is just nothing but d cube p over 2 pi h bar cube times the exponent of I over h bar p dot, let me just write it vi. I will say vi is ri plus 1 minus ri divided by delta t. This is how I define vi. Minus I over h bar p squared over 2m. But this is nothing but the Gaussian integral that we had evaluated before. It has the same form. So that integral just becomes exponential of minus v squared over h bar squared divided by 4 1 over 2m h bar times pi squared pi over I over 2m h bar to the power 3 halves. And there's also delta t. Sorry, here I have a delta t. Everything is multiplied by delta t. Now, I also found where I made the mistake in h bar in our previous calculation. I had forgotten this h bar over there. Now, I will correct it in the lecture, in the notes, before I upload it. Well, let me just rewrite this. If you just make the simplifications, etc., some prefactor, which is 2m h bar pi over I delta t times exponential of minus I h bar, no, I over h bar v squared over 2m, vi squared over 2m delta t. This is what we will obtain for that integral. Now let me just rewrite it ri plus 1, ti plus 1, ri ti. Again, this matrix element now just becomes if you just look at the above part, I already evaluated the p integral, and it just becomes, with some prefactor, I will not write it down, exponential of I over h bar delta t vi squared over 2m. Keep in mind that there is also minus v of ri So if you just multiply all of those, you see this is just one of the matrix elements. And here we have the product of all of them. So that path integral R0 at the time t0, R at the time t, is, I still have integrals over Ri. There's some prefactor, which I didn't write it explicitly. And then I have the exponent of I over h bar, sum over all I delta t, Vi squared over 2m minus V of Ri. But in the limit as delta t goes to 0, that summation is nothing but my integration over time. Oops, sorry, this is 1 over m over 2. 1 over 2 m v squared, v at the time t squared minus v r at the time t. So this is another way of evaluating our kernel, Rt starting from R0, T0, which doesn't involve solving the Schrödinger equation. Now, of course, it will be, just using this to solve, I don't know, the free particle or the harmonic oscillator is, well, kind of useless, because it's much easier to solve the Schrödinger equation for those problems. But one advantage of this formalism is, you see, this expression over here is correct approximately. So that's an approximate, the previous line. That's an approximation of the exact kernel if you keep delta t to be finite. But if delta t is finite, you have a finite number of integrals. And computers are great in calculating numerical integrals. Or what is usually done, for example, on lattice QCD. QCD is the theory that describes the strong interactions of quarks. We don't know how to solve it. We cannot write a Schrödinger equation for it and try to solve it. So it's a field theory. But what we can do is we can calculate this kernel on the lattice. So basically what we do is we first go to imaginary time, as you do as if we are doing statistical physics. Now, one advantage of imaginary time is that, you see, this exponent over here becomes e to power minus h times beta, in a sense. Or not h times beta, but the integral from 0 to beta of the Hamiltonian evaluated at r of beta, r of tau, r dot of tau. Well, the crucial thing is e to the power minus. It's not oscillatory, it is real. And the path that minimizes h, that's the ground state, contributes the most. So rather than trying to evaluate all those integrals over positions, what we do is we just use the interpretation of this kernel as a sum over paths, but we don't calculate all the paths. The path that minimizes that integral are the ones that contribute the most. So we just look at paths that are either minimizes it or that are very close to the path that minimizes it. So using that method, we can calculate approximately our kernel. But we know that once we evaluate the kernel, we know the eigenfunctions, eigenvalues, etc. All that we can study. So on practical application, that's one place where we use this path integral formalism. Another thing will be, for example, we will be studying Aharonov-Bohm effect. The treatment of Aharonov-Bohm effect is simplest in this path integral formalism. Well, we won't be evaluating it explicitly. We won't evaluate the path integral explicitly, but nevertheless, we will be able to derive the fundamental results of the Aharonov-Bohm effect. You can do it also using Schrödinger equation, but in that case, it will be really tough. You will see that using this path integral formalism, the results, I mean, it's just a couple of lines. Okay, questions? So see you on Wednesday.